So dear students, welcome to my YouTube channel PCM Academy and myself Prasenjit Mallik, M.sc in Physics. And as you know, we are in a lecture series of IIT JAM Mathematical Physics and we are discussing matrices. So before going to start the topic, let me tell you that if you are new in this channel, then please subscribe my channel and hit the bell icon also, so that you can get the more updates that I will be uploading various topics based on IIT JAM, Jest, NEET and GATE. Okay. So now let me start with these topics of matrices, and we have discussed in the last class something about eigenvalues, and we have taken a matrix like A is equal to, we have taken a matrix that is A is equal to, I think it was minus 5 2 2 minus 2. So minus 5 2 and 2 minus 2. So this was our matrix, and we have determined the eigenvalues of this matrix, that is lambda 1 and lambda 2. Okay, so we have find that lambda 1 is equal to minus 1 and lambda 2 is equal to minus 6. So these two were the eigenvalues, that is minus 1 and minus 6 for this matrix. And we have used the characteristics equations, and we have got a quadratic equation from where we have find out that lambda 1 and lambda 2. Okay, so now what we will do, we will discuss about how to find out the eigenvector for this matrix for the corresponding eigenvector lambda 1 and lambda 2. So for that case, I have discussed in the theory part in the first video of matrices that if you have a eigenvalue like lambda 1, then corresponding to lambda 1 you have eigenvector x1, and it will follow this equation, that is A x1 is equal to lambda 1 x1. That means this x1 is the eigenvector corresponding to lambda 1. That means you can do it in this way also, that A minus lambda 1 I into x1 equal to 0, and this x1 will be your eigenvector. So now let us take that x1 is x1 is a eigenvector, that is something like this. X1 is suppose 1 2, x1 x2, suppose this kinds of x1 and x2. So let us suppose this kinds of situation, that x1 is equal to x1 x2. Okay, so now let me find out for this A what will be your lambda 1 minus I, A minus lambda 1 I, when lambda 1 is equal to minus 1. Okay, so if we put here lambda 1 is equal to minus 1, in general you have A minus lambda, what we have, A minus lambda I is equal to nothing but, it was minus 5 minus lambda 2 2 minus 2 minus lambda, and if you take this minus as common, then we have got this kind of. Okay, but now if you put this lambda as minus 1, that is if you have A minus lambda 1 I, then in that case you have something like this. Okay, and if you put this lambda 1 as minus 1, then what you will get, you have to put here minus 1. So here will be minus 1 and here will also be minus 1. Okay, so what you will get, this A minus lambda 1 I, A minus lambda 1 I equal to, what you have, 5 minus 1, that is minus 4, and minus, that will be plus 4. Okay, so this is 2, this is 2, and 2 minus 1, that is minus, that is 1. This is 5 minus 1, that is 4. Okay, so it will be minus 4, 2, 2, and 2 minus 1, 1, that will be minus 1. Okay, so it will be minus 4, 2, 2, minus 1. This is your A minus lambda 1 I. Now, if you want to write in this way, that this A minus lambda 1 into x1, that will be something like this, x1, x2. Okay, now this will be 0, this will equal to be 0 according to this equation, that is A minus lambda 1 I into x1 equal to 0. Now you have to multiply these two matrices. Okay, so it will be just minus 4x1, it will be minus 4x1 plus 2x2 equal to 0, one equation, and another equation is 2x1 minus x2 equal to 0. And you can see these two equations are same, because from here you can also find out that 2x1 is 2x1 is equal to minus x2, minus 4x1 is equal to minus 2x2. Okay, that means your 2x1 is equal to x2. Similarly, from here you will get this 2x1 is equal to x2. So what you have this 2x1 equal to x2, and that means x1 upon 1 equal to x2 upon 2. So you can write from here that your x1 and x2, this matrix will be nothing but proportional to 1 2. That means you have to write a constant over here. Okay, so this is your eigenvector for corresponding eigenvalue lambda 1 is equal to minus 1. Okay, so you can write that your x1, that is the eigenvector, that is nothing but k 1 2. Now if you want to find out the value of k, you have to use the normalized condition for x1. So if this is x1, then you know your x1 transpose will be nothing but k 1 2. Now if you use x1 transpose x1, that will be identity. If they are normalized, if you want to normalize this vector, then you have to use that x1 and x1 transpose is equal to nothing but I. So let us find out the eigenvector in the normalized form. Okay, so in that case what you have to use, this 1 upon 2 and this 1 2. Okay, and this k into k will be k square, so that will be identity 1. Now if you multiply these two, you can see that will be your k square into, that is 1 into 1 and 2 into 2, so 1 plus 4, that will be 1 plus 4 equal to 1. That means k square into 5 equal to 1. That means your k is equal to plus minus 1 by root 5. So that will be your k. Okay, so if you want to write this x1 in normalized form, then you have this x1 equal to what is 1 upon root 5, that means plus minus 1 upon root 5 1 2. So this will be your eigenvector corresponding to the eigenvalue lambda 1 is equal to minus 1. Okay, similarly we can find out the eigenvector corresponding to the eigenvalue minus 6 also. So let me find out that thing also. Okay, so now if you want to find out for lambda 1 is equal to, for lambda 2 is equal to minus 6. So what we have a is equal to nothing but 2, so minus 5 2, minus 5 and 2, minus 5 and 2 and 2 minus 2. Okay, 2 minus 2. So this is our a. Now again what we have to find out, a minus lambda 2 into I. Okay, so what this will be minus 5 minus lambda, again minus 5 minus lambda, that means minus 5 plus lambda 2 minus 2 plus lambda 2. Okay, now if you put instead of lambda 2 minus 6, then what you will have, so this will be minus 6 and this will also be minus 6. Okay, now 5 minus 6 is minus 1, minus plus, so it will be 1 2 2. And now if you put this 2 minus 6, that will be minus 4 and minus 4 and minus, this will be plus 4. So this will be your a minus lambda 2i. Now if you put this a minus lambda 2i into x2, if x2 is the corresponding eigenvector, then this will be something like this. Let me take again it as x1 and x2. Okay, and that will be 0. Now if you multiply these two, you will get this x1 plus 2x2. x1 plus 2x2 is equal to 0, one equation. That means x1 is equal to minus 2x2, and another equation is 2x1 plus 4x2. 2x1 plus 4x2 is equal to 0. That means again x1 is equal to minus 2x2. This equation again implies that x1 is equal to minus 2x2. So now what you will get, you have x1 is equal to minus 2x2, that means we have x1 by minus 2 is equal to x2 by minus 1. So again we can write this x1 x2 is proportional to this vector, that is minus 2 and 1. So this is your eigenvector now, x2, and that is k minus 2 and 1. Now again if you use the normalized condition, you will get again directly, you can evaluate this value of k directly by squaring and adding these two. Okay, so minus 2 square plus 1 square, that will be again 5. So you will get x2 is equal to plus minus 1 upon root 5 into minus 2 1. So you can find out the normalized condition just by squaring and multiplying, squaring and adding these two, and by taking the square root. Okay, so this is very simple, you know, and that is you can, otherwise you can use that x transpose x is equal to I. Okay, so that is also the normalized condition. Otherwise you can understand this normalized condition by using the ordinary 3-dimensional vector algebra that you know in ordinary 3-dimensional vector algebra. Suppose you have two vectors which are normal to each other, or normalized, which are normalized. In that case you have just, suppose one vector is in component a1 I cap plus a2 j cap plus a3 k cap. Okay, and another vector is, suppose you have b1 I cap, or if these two are same, then you have just a1 I cap plus a2 j cap plus a3 k cap. Okay, now if you take the dot product of these two, then you will get a1 square plus a2 square plus a3 square. Okay, same as here also. So you have two things, one is 2 1 and another is minus 2 1 and another is minus 2 1. So if you multiply these two, something like a dot product, you will get this 2 square plus 1 square, that is 4 plus 1 is equal to 5, and if you take the square root of these two, then you will get root 5. Okay, so this is how you can find out, okay, the corresponding value of k also. Okay, so this is your eigenvector x1 and x2. Now let me take one other thing also, that these two vectors, what we have got, first we have got x1 is equal to 1 and 2, and then we have got x2 is equal to, let me ignore this proportionality constant now, and x2 is equal to minus 2 and 1. Okay, now if you take the conjugate transpose of this x2, that will be x2 dagger, that will be your something like minus 2 1. And now if you multiply these two, what you will get, if you multiply these two, you will get this x2 dagger x1, that will be minus 2 1 and 1 2. Now if you find out this minus 2 plus 2 is equal to 0. So that means this x2 and x1 are orthogonal to each other. X2 and x1 are orthogonal to each other. And if this x1 and x2 are orthogonal to each other, and if this x1 and x2 are also orthogonal to each other, then these are linearly independent also. As you know again from your ordinary 3-dimensional vector algebra, that if I and j, okay, if your I and j are two vectors, then you can see that if you take the dot product of these two, you will get 0 always. And I and j are also linearly independent because they are perpendicular to each other. Okay, so similarly you can say from here, okay, that this x1 and x2 are orthogonal to each other and they are linearly independent also. So always you have to check the orthogonality condition when if you want to find out the vectors are linearly independent or not by using this kinds of dot product. So you have to just take the transpose conjugate of these two of one and multiply the other, and this is also called inner product. Okay, This is also known as inner product. This is also known as inner product. Inner product. Okay. So if your inner product is 0, okay, your inner product is 0, then you can say these two vectors are orthogonal to each other and they are also linearly independent.